So in the first lecture, I started by a question about how to design computers. You could use the biological inspiration or inspiration from mathematical logic. And I mentioned that mathematical logic won. And the question is why? And one of the reasons why is because with mathematical logic, you can reduce complex tasks to combinations of simple tasks, which is a process called programming. And if you have new ways to solve simple tasks immediately, you find a new ways to solve a simple task, and immediately it benefits everybody, everything. So somehow it's a very good way to work as a group and to develop an engineering culture. That was much better than doing perceptron. You have a perceptron, you can put something in front of the retina, but then you do what? So reducing complex tasks to combination of simple tasks is an engineering necessity. And if you look, for instance, other engineering disciplines like buildings, you see every country is a bit different, but you're going to find basic building blocks like electrical gear or electrical things that are repeated everywhere. And if you were to build a conference room like this one to have the optimal one, you probably wouldn't do exactly this or use this exact gear. You could optimize something differently, use only 172 volts for the lights instead of 220 or 127. So you would go out of the convention and do something maybe slightly better for a particular purpose, but that would be useless. So this dividing the work into having simple modules that you can reuse and you can combine, and it's actually something good. Now, if you look at simple learning tasks, like tasks that you see in an IPS paper, an ICML paper, 8 pages, something that fits in 8 pages, classification, regression, clustering, multi-arm bandits, and things that you can analyze easily. Well, and you have complex learning tasks like reading checks, where you have to deal with the segmentation, finding where the characters are, which of the block is the amount and everything, recognize the amount, segment it in characters, then interpret the sequence of characters as an amount. Well, it's already a lot more complicated. If you want to parse visual scenes, you have to find objects, recognize them, and understand their relations. This is a lot more complicated. And it's not just a classification or regression, it's something else. Or composing personalized web pages, well, you have to deal with feedback, meaning that if you show a particular web page with a certain attempt to compose it, you're going to get feedback in terms of clicks, of reactions of the users or whatever, but only for that page, not for the other ones. And then that's a quick feedback. You're going to have a low feedback, a small one, where if you show always the same kind of things to the users, they're going to fatigue or they're going to have a long-term effect, they're going to change their opinions. And the other partners like advertisers or people providing the content of the web page are going to change because their return on investment is going to be different. And if you don't understand all these long-term interactions, you're going to do something crazy. And that's very complex. And no, this is not a multi-arm bandit. This is way more complex. Natural language understanding, well, it's even hard to define. You can define subtasks, but it's hard. And strong AI, why not? It's a learning task, but we have no way how to start. So if we want to go to the difficult task and eventually maybe even do strong AI, we have to understand how to reduce complex learning tasks to simple learning tasks, or have something that brings a kind of engineering modularity that we want to have. Now, should be honest, in machine learning, there is one domain in which you have a kind of little bit of that. It's Bayesian inference. And in fact, I think the appeal of Bayesian inference is because it provides a language to describe complex models with basic primitives. You have generic algorithms, they're too expensive, but they're generic. And well, it's true, you can do some things there. It's quite interesting, except there are things you cannot do. First, you have computationally costly algorithms, and people do dirty approximations, and they study the algorithm instead of approximations. It's a bit strange. Second, they don't do causation properly, which can be important. It's a different kind of reasoning causation. You can reason with correlations or reason with causations, and you're not going to reason exactly the same way. And depending on what you do, you have the right way to think, to reason about your problem. And they're not very good at perception. Like the kind of thing that convolutional neural nets are doing very well, they don't do very well. So somehow you have to see that you have different ways to combine things together. And in my view, and it's my view, they're connected to various ways of reasoning. They reason about correlations. Okay, Bayes rules is a perfect way to reason about correlations. You want to reason about causations, you need to do something else. You want to reason about space and objects and how they go in front of each other. If you do that with Bayes rules, it's going to be very, very tricky. So how can we do this with neural nets, and can we actually reach this kind of reasoning and inference level with things like neural nets, and where does it go, where does it take us? So that's interesting because we know that there are some kind of neural nets that we don't understand very well that do pretty well at reasoning at various levels. So is it possible? Is it a good model? Is it something we can actually implement or not? And there are a lot of open questions there. So I would like just to show a number of leads that come from recent research and from dreaming on a little bit sometimes. So the first one is deep network for complex structure problems. Take an example, reading check amount. So that was something that was done in the mid-90s in AT&T. So here is a check, not very interesting check, but you see they're full of annoying things. Like you have an amount there. This is a typical business check in the US where the amount can be anywhere. You have stars, stars, stars because it's cool and people doing accounting like this. You can have things like not to exceed, valid for any amount, not to exceed $10,000, and this is not the amount. And you can have the text itself that should match this. And you have all those kind of things, little images in the background. This can be printed with an awful dot printer matrix that toc, 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 and so no character is actually connected. And then you have handwritten checks where the amount is more placed in a standard location, but people write very badly. So, okay, let's go direct. Collect, scan, check images, all the check. Collect the outputs, the desired outputs, a positive number, and let's train. The problem is that we didn't really try to do that. Is it possible? I don't know. Maybe now it's possible that we have a faster computer, but it was certainly not possible. So you would need a lot of labeled examples just for simple things that to realize that this is the amount and not that, and not that, and that somewhere there is a date that looks an amount, but it's not an amount. And excessive computation time as a result. So you want to decompose the problem in a way that's more feasible. And so at that time, we did it in a very engineering approach, say, identify subtasks, locate the amount field, segment the amount field into isolated characters, recognize isolated characters, translate character strings into amount. Now, of course, if you do this in the traditional computer science, you do each task exactly right. You have the amount field, only one, that's the correct one, and then you can do the next one. If you do some learning things, well, no task is going to be exactly right. You're going to have one amount field that with a certain error probability, and maybe a second one, and maybe a third one. And for the segmentation, you're going to have segmentation hypothesis. You need to backtrack, you need to move, everything's connected. That's a bit annoying. But anyway, you can approach it with the engineering way. You define a model for every subtask. So in that case, a fairly complex recognition model to recognize the characters. There were convolutional nets, and very highly engineered the location and segmentation models to try to find what could look like an amount and everything. You collect data for everything. So you check images, you have somebody cut the amount, cut the characters, and label them. It seems costly, but if you do that in a real problem, it's not that costly. It's somebody working for 1 month, fine. And then you have these interactions between all these levels. That's a bit annoying, that what is a good amount field? A good amount field is something that contains nice characters, which happen to be digits, which happen to be interpretable as an amount. And something that contains things that look like characters, like this, let's say American style. Well, this is not 8 million, this is a date. So you have to go to the very end to realize that you don't have the right amount. So there are several training strategies, assuming you collected data for everything. The independent training, where you train each submodel separately, you hope it does the right thing, and you go on. Sorry, this annoys me. And well, it's sort of going to work, but you can do better. You can do sequential training. So you pre-train independently because it never hurts. Then you run until a certain subtask, submodel, and you label the outputs of the submodel. So now you're going to train the next submodel on the outputs of the previous submodel and exactly what it gives. So somehow the next model is going to be tuned to the kind of mistakes that the models below can do. It's a bit better. And there is something even better, which is you pre-train with sequential training, and then you train all your system like a deep multi-layer network by computing gradients all over the place. And you can do it if everything is differentiable and everything. But you still have the problem that you need to track multiple hypotheses. You do backtracking and everything, which is annoying to do in the context of a learning system. So to try to solve this, we moved from something like a multi-layer network where every vector here represents a decision made by the upstream layer that you send to the layer below, to actually graphs. So each graph there, each path in a graph represents a combination of hypotheses that receive a score. And then each transformer transforms them into a slightly different graph with more refined hypotheses and everything. And I'm going to give examples of these kind of things. And you can track the scores, track the gradients, compute the derivatives exactly the same way, and go on. So the problem I want to deal with here is a word reader. So I have this little image that represents a sequence of digits. And essentially, I want to find the right segmentation. I want to say whether this is a string of digits or not. So I'm going to segment it, and I get something like this, for instance, where every path covers all the pieces of int with various ways to cut it. So the correct one is 3, 4, 2, but I could have this, or this. There are legal ways to segment this digit, this sequence of characters that seem consistent with the pixels I see. And each of them could have a certain score. Now I'm going to apply a kind of recognizer that's going to give me a score that whether this is each of these images is a digit. So let's say the score gives low penalties to well-formed characters. So this is a well-formed character, it's penalty 1. This is a well-formed character, it's penalty 2. I forgot what the 0.7 means. It meant something. It's 15 years ago, so maybe I forgot. So 3 is this, and okay, 1, 2, 3 is actually the recognized character, and what's in the bracket is the score. So this is a good one. This it says is 8, but has a bad score. High score means bad. And this is a decent 4, and this could be a 4 with a relatively high score. And when you have this, you can run a Viterbi algorithm to find the path with the smallest score, and that gives you the segmentation and the recognition you want to have. Now the question is how to train this. And I need to make a little digression. There are typically 2 ways to train a classifier, at least when you're in a probabilistic setup. Generative or discriminant. And it's interesting to understand how they're different. So in the generative training, you estimate the distribution of your patterns and classes, the joint one. And to do this, you define the model. So P of xy is a number that's going to be parameterized by some w. And the model is such that the sum over xy of pw of xy sum to 1. So it's a probability. It's a joint probability. Then you maximize the likelihood, or the log likelihood. So you take the log of this function over the examples, you maximize this. Now, if you do discriminant, you want to estimate P of y given x. So you define a parametric function that takes x, y as argument, and a parameter w, and normalizes differently. Sum over y of this function is 1. And then you optimize the likelihood. So this looks the same. This looks the same. So the difference is in the normalization. And depending how you normalize your scoring model, is going to be generative or discriminant. Now, you have another problem, is that when you combine models together, bad things can happen, because nothing tells you that when you combine several models to look at it as a large model, it's a well-formed model that has the right properties. So if you combine something like a generative hidden Markov model, so this time these are the states, and I'm going to say that right? I define my function Pw of xy as being the sum over all the sequences that are compatible with the sequence of digits I know that's y, of the product of the transition probability times the emission probabilities. Fine. This has been done. It works nicely, everything. Now, if you want to do it in a discriminant way, you're going to say Pw of xy is P of y given x and w, the parameter. It's going to be the sum over all the paths that are compatible with the class I want, of the product of some probability to go from one state to the next given the input. So you can see as a classifier, given that I'm in state st minus 1 and I observe xt, what chance I have to go into state st. Now this sums to 1, so the sum over the st should be 1. So we should have a model here that's normalized. The probability of all st, the sum of the probabilities of all st, all possible values of st given st minus 1 xw should sum to 1 by definition. But it's a very bad idea, because if you have a graph like this, where, for instance, you're in that state, and this graph has just one transition to that state, well, when you normalize, there is just one possible transition, its probability is 1. So basically, the fact that this is a bad digit, doesn't look like a digit, is not going to be taken into account because of the normalization. So somehow, when you do discriminant model and you combine discriminant models, if you do it by looking at them as probabilistic models, you do something silly that you ignore negative information. If you have a path that goes to something that, so you make decisions that force your decision to follow a path where at some point there is something implausible, but that's the only solution locally, you're not going to penalize for that. It's a bad idea. I don't know if it's clear. This puzzles a lot of people, so it's complex. Yes?
Why not just find the shortest path?
Okay. The problem here is in the modeling. You model something like this, a discriminant Markov model. If I do it on a path like this, when I'm on, let's say I'm on this node, I have only one possible transition by definition of the model itself, of the transition state. So here, I have only one possible value of st, and therefore its probability is 1. Therefore, the fact that this is a good or a bad digit is not something that's going to have an impact on the final score, because I normalize it away.
Yeah, but if you go 2 slides back, you can't skip all these modelings and just...
If I go back, I'm going, so if I look at the score of this path, the fact that this is a good or bad digit is not mentioned. It doesn't have an impact. So basically, what's going to be the best path is going to be defined by what I see at the beginning of my sequence, at the end of my sequence, but not the center. If I force my system, because of the structure of the segmentation graph, to go through things that are not digits, if early decisions give good scores to something that takes me into non-digit, where I'm forced to go through non-digits, and then I have good scores at the end, the fact that I go through these non-digits are not going to be penalize me if I look for the best path. Oh, I promise. Maybe I didn't explain it right away, but it's true. Yes?
The short version of this is that you change the layers to be generative and not discriminatory?
Well, the short version of this is that if you compose a discriminant model as composition of local discriminant models, you lose information, because the local discriminant models have a normalization that's a loss of information, and sometimes it's the information you want. So it's not that they have to be generative. What's generative or discriminant is the global normalization of the stuff that's going to make it discriminative. But having this intermediate normalization is something that has a cost. So one way to do this is to say, okay, if I use probabilities, I'm supposed to normalize. Things are supposed to sum to 1, and I have to say what is supposed to sum to 1. But in fact, the only normalization I want is at the very end, because I want my whole system to be generative or discriminant. So instead of using probabilities, I can use measures, which they add and multiply probabilities. They're just not normalized. So you speak about scores, not probabilities anymore. You say the score of a path is the product of the scores of the arcs, and the score of a subgraph is the sum of the path scores. And at the very end, when you want to maximize, you normalize according to what you want to normalize on. If you want to be discriminant, you want to normalize over all the possible classifications or amounts or whatever. In the case of check, it would be amounts. And you maximize the likelihood. Now, when you can do this, you have, I said, the measures that are positive, they add and multiply, so it's R plus multiply. But you can go into log space, so you can take the log of the scores, and it would be R, the multiplication becomes a plus, and the plus becomes an operation that we call logad. So let me write logad for the fun of it. Say that A plus B equal log of exponential A plus exponential B. It's just a mapping. I just applied I just reasoned with the logarithm of probabilities instead of the probabilities. And this is almost like a max, in fact. Or you can replace the logad with a maximum, and you have the same algebraic properties and the same kind of algorithm overall. So it's quite amusing that you have various ways to score things. Some are interpretable probabilities, some are log probabilities, and some are actually extremes that give rise to things like Viterbi training and other things like this. So let's do that. So I'm using the max thing here, the max plus. I go to a segmenter, I have these things. All these things are going through little convolutional neural networks that gives me various answers and various scores that we had last time. So now I have this graph here with various. This, for instance, could be a 3 or a 5. A 3 with penalty, the penalties, 0, 1, 5 with penalty 2.3. This could be a 4 with penalty 0.4 or a 2 with penalty 1.3. So I have all this graph here. Now I know that the desired answer is 3, 4. So I'm going to select in this graph all the paths that are compatible with the answer 3, 4. And I get something like this. Then I'm going to score the subgraph by taking a Viterbi and taking the max path. So it's a max scoring. And I have a certain score here. That's just here, 0.7. Alternatively, I can take the full graph and score everything. Take the best path in there, which is the best recognition. It would be 3, 4, 1 in that setup that my current system is doing. I can add them to get the score of the path and have the score of the other things. And my goal would have to be this score as close as possible. With the max, actually, it's not completely consistent. With the log loss, it's actually consistent, but that's a detail. So now I have my loss function, which is the difference between these things, or this difference, because I'm in log space, is the same as this ratio. So, sorry. So this is the log of the probability of recognizing 3, 4. And this is the normalization, which is the log of the probability of being in the graph. Except that I use the max. OK, fine. Now I have my loss function. I want to compute the gradient. So OK, that's the +1 here. The gradient of the loss with respect to the loss is 1. Then this is a difference. So my +1 minus 1 by the chain rule. And I go down. And this is an addition. So I got my +1 and +1 here, and -1, -1, -1 here. Then this is only on the path I took, which is +1, +1, 0, 0. And here, and when I go down again, I can see which components of the path have gradients. So for instance, I would like to increase the output of this network here. This is more a 4 than I thought it was a 4. And this is less of a 1 than I thought it was a 1. And this is less of a 1 than I thought it was a 1. Then I can train my networks. And I can do down. I can even train my segmenter if I want, by backpropagating the gradients that way. Now, of course, you can do that on more complicated things. But first, there is a connection between this and the conditional random field. The cost function, this late normalization, is the same as the CRF. This is a hierarchical model. It's coarse to fine. I'm going to start with relatively coarse things like segmentation, then recognition, and then finer things. And inference is trivial. Inference is trivial because it does something that you don't see in a hierarchical CRF. Yes?
Is this model explained by the
Yes, it solved the discriminant training because the normalization is late. Because if I have something like this that's not a possible character, it's none of the classes I know, it's still going to have a low score. Well, if I was to normalize it, I would erase this information saying it's an average score. But I just didn't normalize, meaning that when I get the outputs of manual networks, they're not normalized. Nothing forces them to be normalized. Which one? This one? Next one. That one? That one? Yes, at the very end. That normalization, that ratio here, so you have to move it from R plus times to R max plus. So the normalization becomes a subtraction, okay? It's here. So that's the score of the correct answer, of all the paths that are consistent with the correct answer, and that's the score of all the paths together. And I subtract them, so that I normalize them. Yes?
What's the difference between that normalization at the end and the global normalization in the generative model?
In the generative model, you don't have to do that. That's the trick. In the generative model, when this and this are normalized, this is guaranteed to be normalized and sufficient. So basically, when you do something like a hidden Markov model, the deficiency doesn't appear. Or more exactly, if you have a generative model, you only use positive information. You only try to model what belongs to the class. And you're not trying to say this doesn't belong to the class. You say this doesn't belong to the class comes because you have a background model or you have a generative models for all the classes and you try to find which one is the best. So the fact that you don't do that at the local level is not a big penalty. But if you do a discriminant model, you're trying at the same time you're trying to find the boundary. You try to find the difference between what's in the class and what's outside of the class. So you want to use negative information. So if you rig your discriminant model in such a way that at the local level you cannot use negative information, you're basically undoing what you wanted to do. So you have to build them differently. And the way is not to normalize. So yes, it's actually tricky. It took a while to actually understand this.
Can't negative information be incorporated in the generative model?
The what? The
negative information?
In the generative model, it's against the spirit of a generative model. The generative model is not doing that at all. So the global cost function you're going for the generative model is not going to even capture this. So somehow what you see here is that when you combine models together to make a large model that you want to train globally, if it's generative or discriminant, things are going to be subtly different. It's easier in the generative setup. It's more complex in the discriminant setup, and the best solution in the discriminant setup is actually to get rid of the normalization, which is what people did in the CRFs sometime after that. No? Yes?
And so looking at the overall picture, so there's some input and some output. It's called the input X, the output Y. Then the whole thing is learning P of X comma Y, or is it learning P of Y given X?
P of Y given X.
So, but it doesn't care for the distribution of X.
No.
So it wouldn't change.
It cares for the distribution of X in the sense that where you have more examples, the estimation will be more precise. But it estimates P of Y given X.
Because, I mean, there's a certain distribution of the digits, and so since during the training data, it will be reflected that there are more ones and twos and threes and fours.
Well, just like OSVM. OSVM is a strictly discriminant system, even more discriminant than this because it's really the boundary, not the posterior probability. And of course, if you have more ones than two, it's going to shift a little bit the boundary, but it's still going to find the boundary.
I mean, in the context of this causal, anti-causal learning, and that's what.
Yeah, I didn't think of the causal, anti-causal aspect in that setup, so I can't really comment. But if you have good ideas, I'm very glad to hear about them. But yeah, okay. So yes, and cheap inference. If you have a hierarchical, so okay, how I'm going to explain this. I'm first going to show two graphs. Some people draw a hidden Markov model like this. Okay? Some people draw it like this. And it's completely different. This graph is the Bayes network graph. It tells you that at various times, time 1, 2, 3, this could be in a certain state. The state at time t plus 1 depends on the state t, and the observation depends on the state and the state only. These circles are not time. They're the various values of the state variable. And this tells you in time what can do. So you can loop 3 times there, meaning that you go 3 times in that graph, and then just 1 time here, and so on. So traditionally, people in the Bayesian network do this, and people doing speech, they look at them that way for a number of reasons that tell you that these graphs explain different things. Now, if you do a hierarchical CRF, so you have to look at the Markov random field, it's going to be a beast, so undirected this time, like this. And then you have another layer at a higher level, and so on. So the problem that you have is that you have these loops here, which make the inference painful. And then, of course, it's annoying. Now, one thing that you cannot really express in this graph is that, for instance, this is a coarse thing. Like this is locating an amount, this is recognizing characters, and this is interpreting the result. And of course, if this state says that your field is in a particular spot, you would like the segmentation to segment a character in that particular spot. So when I'm doing things like a graph transformer network, I have an additional constraint that's not very visible on this kind of graph, that the value of this variable and the value of this variable are constrained in a way that's hard, not probabilistic. So this constraint actually makes the inference easier. And this is why I can do the inference with a simple Viterbi in that case. Anyway, so that's just to comment on the difference between these things. So there is a big connection between the two. So here is a check reader. And this is a real thing. It was developed in 95, 96. There was a team of, easily 12 persons. Good people. It was not easy. It was industrially deployed in 96 and has processed about 15% of all US check for nearly 15 years. So it really worked. It's really a real thing. And you start with the check, and you have what I call the check graph. Input node, output node, just one arc, and the image is attached to the arc. Then you look at fields. So you have various field candidates, like this one, this one, this one, each with a score. Then you segment the fields. So for instance, the upper path, which is these things, is going to have something where the images are going to be $*345, but then the other paths are segmented as well. And this is what I mean by the fact that the constraint. If in that graph my little stochastic daemon is on the lower path, I'm guaranteed that I'm on the lower path here as well, which is not something that happens when you do a standard hierarchical CRF. And then you run your character recognizer, and each of these arcs, which was an image, become a bunch of arcs with potential labels and scores. Then you're going to compose it with a grammar, and I'm going to discuss that a bit later, and you get a new graph where the paths are possible interpretations of the sequence of digits in what could be an amount, and then you do Viterbi to find the correct amount. And you train everything more or less separately. You put them together. You train them sequentially to try to adjust them. And then you try to put together. And actually, we train the top part up to the top of the character recognizer globally using gradient from the top. And that actually makes a difference. So the training architecture, is the same kind of thing where you have the same composition. And at the very end, you start splitting in two to compute the numerator and the denominator. And use the forward algorithm instead of a max because we wanted something closer to probabilities. You compose in a way that's going to select the paths that are associated with the correct answer, the correct amount, not the correct sequence of characters. It's really the correct amount. Then you score this, and then you compute the normalization, you have a difference, and you backpropagate to that thing. So the system without all these things before was, the goal was to say that we want less than 1% error assuming that we can reject things. So the classifier system would just say, I classify this, I'm sure, with less than 1% error. I reject, and the human must look. And then there is the error, of course. And there are other validations that make that the 1% error is acceptable. So the important number is the number of correctly classified at 1% error. So different on machine print and the mixture of hand-print and not. And on machine print, which are the ones with complex layout, we went from 68% correct to 82, which is a big difference. And that was enough to take the mixture from 45 to 50, which was the threshold for deployment. And over the following years, Patrick Hafner rose that to about 60%. And then it ran for 15 years with no improvement until... the reason why it stopped running is because the scanners at the time were 200 dpi, black and white. And 15 years later, so at the beginning, there was the most accurate system. At the end of the 15 years, they had other systems using higher images in color, 600 dpi instead, so you have better information. But they were slow. So this was the fastest system. So they would run this on everything and run the expensive system on just the rejects. And at some point, the expensive system became cheap enough that they could use it. So that was the end of the system. But if you know that at that time they had 5 billion checks per year in the US, 10% of this is about 500 million checks every year for 15 years, quite a lot of checks. I don't know who got the money. Anyway, so what time is it? I started at 2 and I'm halfway. Okay. Now there is this thing that you have this brick now that takes an input graph, an output graph, and a transducer. So that comes from the graph transduction theory. But what you can say is that the transducer is a kind of abstract thing that's defined by a matching in the building rule. And you have ways to define a generic graph transforming engine that is going to involve matching which path here and which path in the transducer are going to match. In the case of the gamma, it's because they have the same label. And then what kind of path you're going to build in the output graph. So by specifying these two things, you can specify what the transformation is going to be. So in fact, the amusing thing is that all these boxes run exactly the same code except for these two match and build methods. And all the backpropagation is completely generic using exactly these codes. So that was quite a cute program. We had fun. To some extent, until it becomes deployed and then it becomes hell, but that's another story. At that point, we just went away. AT&T Bell Labs was split between AT&T, Bell Labs, and NCR. So the people who did the research went to AT&T, the people who did the implementation went to Bell Labs and Lucent, and the people who were selling them went to NCR. So they're probably the ones who got the money in the end. But we didn't have to fix it. So it's good that it ran for 15 years without too many problems. And it was written with the esoteric Lisp that you've seen that compiled to a C that's completely unreadable. And of course, they couldn't use the esoteric C, so they had this bunch of C code that was completely abscons. That was very short because everything was the same code. You know, all these boxes are the same code. And so, it was our place to fix, but anyway. But the thing that you can do these things, and you can do highly structured systems using neural networks, and they're founded on sound principles, and they're structurally very complex. They go around the number of inference issues in ways that are interesting. I told you before that Bayesian inference had very generic properties of having a framework in which you can define complex model using simple elementary things and apply generic algorithms that happen to be too slow. By changing a little bit, you can do the same thing at the perception level. It's quite amusing. Yes?
I didn't quite understand, how do you feed this information from the graph to the neural network?
From the ground? From the graph. Let's go here. So I take this. I have a neural network in the forward path, took the image 3, and produced this score 0, 1 for label 3, 2.3 for label 5.
So anything on the arc goes to a network?
Every arc is one of the outputs of the neural network that was run on the corresponding arc in that graph, in that case. instance of the neural net, they share the same weights, by the way, took one of the images that's on the segmentation graph and compute a bunch of scores and potential labels. And then the graph transformation engine produces, in that case, this one is a simple one, produces between two equivalent nodes a series of arcs. Each one represents a possible recognition of this character. So you have an invariant that if you take a path here, you get the segmentation hypothesis. If you take a path here, you get a recognition hypothesis together with the segmentation.
So you need that many neural nets with as many parts?
It's actually the same that you're going to run several times. But you need to keep all the activations because you're going to use them for the backpropagation. So there is quite a lot of bookkeeping to do, and it's dynamic because the arcs are going to change, the number of invocations of the same neural nets are going to change. You need to track all this. So it's not so easy to code, but it's doable. It's actually simpler than what was done in the old system, where all this was implemented with more or less intuitive logic, and there was a formalization of what we wanted to do. That was actually simpler because, as I told you, the essential code of all these books was the same. Then when you do backwards, you compute the gradients, then you have the gradients here. So that's 0, minus 1, 0. The gradients are the output of the neural net. Then you can backpropagate to each instance of the neural net to get the gradient with the weights. You sum them to get the total gradient on the shared weights, and you can update your neural net. But then you can go back and update the parameters of your segmenter. Or when you have a grammar, you can update the parameters in the stochastic grammar as well. So you can do all these things in a unified setup. So sometimes I want to... I'm vain, and I said that was 5 years before the CRF, but yeah, I'm sorry, I couldn't resist. So, okay. So now I'm going to change gear and look at something else, another aspect. The retargeting learned features. So take the ImageNet network. You take the Krzyzewski code, you train it on ImageNet, and you train it as best as you can on ImageNet. You chop the last layer. The last layer is the one that outputs the ImageNet categories. You append a new last layer that's with random weights, but this time it's the Caltech 256 categories, another data set. You train your network on Caltech 256, and let's say you fix the weight on the ImageNet, because that way you don't have to run the GPU and you just record everything, and you observe that it works. That's very important because there was a paper by Alyosha Ifros, where he used a system that was essentially linear, like SVMs on uncrafted features, and tried to see how SVM with uncrafted features trained on the database would generalize on another database. It was a catastrophe. That something trained on ImageNet would work very poorly on Caltech 256 because the images are slightly different, or Caltech 101 would be a catastrophe because they're black and white. And so his conclusion was that you cannot transfer machine learning very easily from one data set to another, or that our data set is biased in such a way that it's very difficult to have a generic system. When you do it that way, well, the last layers, they don't generalize because they're specialized, but all the layers before, they actually work quite well. Now, there is a question. Should we keep the weights fixed in the ImageNet train layers or train them again? And I'll let you mull the question. I'm going to give hints for an answer later on that was at the very beginning of the lecture. What kind of results you get that way? So these are the kind of state-of-the-art on Caltech 256. This is the accuracy, and this is the number of training images per class. The thing is that when you do this, with 6 training images per class only, you reach a state-of-the-art result on Caltech 256. With 1 is not too good. With 2, you are already equivalent to something that has 15. And so it's quite good. So you're in a situation where by training something on a large data set like ImageNet and getting features, you plug a new layer on top with new weights, and you train on slightly different tasks, but similar thing. And you need very few examples. So any ideas about whether one should keep the weights fixed or not? No? Okay, so let me try to go very early in my... You remember that thing, that network, that old network from the 80s? I show you the story of the dog. It's quite a cute story. But you can see it as something different, you know. You train your network and you only have one kind of land animal, it's a dog. So everything is a dog, you know, everything that looks with legs is a dog. And when you add a new input to your system, which is a goat, well, the goats are the dog at the beginning. The system says goat is a dog. Then you train more and then you recognize that a goat or a pig is a different thing. Okay. And this one was changing the relation. I start with training only with relation is. So at the beginning, you know, is yellow is very important. You know, this thing is yellow. So a sunfish, a daisy, and a canary, they go in the same group. And the robin and the salmon, the rose and the sunflower, they're sort of pinkish. They go in the same group. Then you add new relation like either or as other category, can live, can grow, and so on. And when you train, all these representation reorganize and you get the right clustering. So the thing is that when you change the task, even though this was not that good, you get a path to the new one. So yes, my belief is that you should actually let them train again, because when you have a new problem, you might actually do something interesting. It's my belief. It's harder to do, yeah. Yes?
So when you're training the neural nets, you're actually showing them like a specific subset of the data that...
In that one? No, this is a specific experiment where I start by training with high frequency of is thing. The idea of McClelland, and actually it was Rummelard, sorry, was to try to see the same kind of phenomena you see in the development of children. So at the beginning, you show them only dogs. And when they see a goat, they say dog, dog, dog. And say, no, it's a goat. You have a new class that appears. And then it has to readjust. And the readjustment follows certain properties that you can measure, you can empirically evaluate them, and you see the same kind of phenomena in these networks. And the reorganization is the same by adding not an item, but a new class of relation. You go from is yellow, is a color, to can do something, or to either to get a kind of taxonomy. You have a reorganization of the internal representations that eventually represent this taxonomy. So my feeling because of that is that when you do these things, you probably want to train on the input layers, except that for ImageNet it's complicated because you have different implementations and GPUs and all the engineering that comes in the way. So that's why people don't do it. But in another example I'm going to give, which is the natural language system that I'm going to describe later, training everything again actually helped. So in the end, that tells you that you want to use different tasks. If you have a particular task with few labels, maybe there is another task where you have a lot of labels that you can use. And in fact, you can think about what is the price of a label. Suppose there is a task that's interesting. You know, you have a business interest. People want to build a classifier for certain things. They want to do it because the labels are scarce, because they're costly to get. They hope for a cheaper way. So most likely, for the tasks that are interesting, the labels are going to be scarce. Otherwise, the task is not interesting. The claim is that in the vicinity of an interesting task with scarce labels, there are a lot of tasks that are not so interesting in terms of economical benefits, but they could be, so they have a lot of labels, but they could be put to good use. Let's give a couple examples. Face recognition. So that's due to Matt Miller in NEC in 2006. Suppose you want to recognize the faces of 1 million persons. How many pictures are you going to get per person? Okay, take Facebook and everything, 5, 6? Oh, 6. Kind of the same number of Caltech, you know. Maybe 1, fine. Now, you can define another task. You take two face images, and you wonder whether they represent the same person or not. It's not that it's less interesting. It's not really the task you want to do, but intuitively, it's going to be the same kind of features. To tell that two persons are the same or not, you want the same kind of features. But you have plenty of examples. You know, if you have two faces in the same picture, they're likely to be two different persons. Actually, you have two exceptions. You have the case of mirrors, because sometimes you have mirrors, and the case of twins, because it depends how you want to label twins. But you can somehow quantify this exception and get an idea. Now, if you take two faces in successive frames, they're likely to be the same person, maybe with completely different orientation of lighting, so it's useful. So you're going to train a system that's built, let's say you have an image, let's say you have a convolutional feature extractor, and second image, the same feature extractor with the same weight. You get two representations of the images, and then a comparison, like a cost distance and everything, and say yes, no, it's the same, not the same. You train that thing. And you can train it on a lot of data. Then you're going to shop everything, you're just going to take that block here, this representation, and just going to train a classifier on top of this. And you get pretty much the same thing as the Caltech stuff, you know. A couple examples are going to be enough to train this classifier on these features because these features do the hard thing. They do the lighting invariance, they do the translation corrections, they do the little rotations, they do the hard things. The features in that space can be decoded almost linearly because they could be compared almost linearly. Now I have a more complicated example, which is NLP tagging. That's Ronan Colobert, Jason Weston, and others from 2008 to 2010. So the interesting tasks were a lot of NLP tagging tasks that are from the book. You know, NLP, there is a number of data sets that have been produced, tree bank, prop bank, with a lot of labels. And they contain about 1 million words. And labeling this data set is a massive endeavor. And the auxiliary task is what I call the word compatibility language model. What we want to do is take a sentence segment and say whether the central word is in its place or not. Is it a good word that goes at this position in the place? So you take Wikipedia sentence segment, and you have 600 million of them. But maybe more now, but at that time 600 million. And you take a segment, let's say, of 11 words, and you say that's a good sentence, that's a good segment. Then you replace the center word by something random, and you say that's a bad one. And now your training is that you want the score of the bad ones to be less than the score of the good ones with a little margin. It's a ranking loss. And you can train that on a lot of data. In fact, Ronan, who did that, was training on a cluster, so each cluster was a slightly different variant of the system. And at some point, he went on vacation and forgot the job running on a mixture of stuff. Instead of running 1 month, it ran 2 months. And instead of running on 600 million Wikipedia, I started to go over the data set and go into the brown, so it went over 1 billion examples. And it worked better. So it's one of the cases where it's absolutely clear that going from 600 million examples to 1 billion examples worked better, and being better on the auxiliary task was better on the interesting task. So here is the kind of system. The input is a sentence, a full sentence. Each word is encoded in 0-1 mode with a hot unit. And you project this by a linear layer into a code. So basically, the weight associated with this word is going to be a representation, a little bit like the Normalized network at the beginning. Then you have other inputs that represent the position of the word of interest. You say, I'm interested in tagging this word in relative to these other words. And the tasks are things like part of speech, non-entity recognition, chunking, semantic role labeling. And the language model is trained exactly on the same thing, except that you first train the language model, then you take the embeddings of the language model, you put them into these things, and then you train everything together. So I'm going to try to run it. No, don't change anything. Okay. Okay, I hit here. So it was trained on things like the tree bank, which comes from the Wall Street Journal, so it's relatively literary text. And when I try to come with a sentence that is literary, I don't find it enough, so I take my New Yorker. It's the one from next week. It wasn't trained on it. So it's tested. I open a random page. I try to find a sentence that's not too long, because otherwise it's going to be boring. Yeah, well, the lifestyle of an elite athlete rivals that of an inmate but it's not complicated enough sentence. I want one that's complicated enough so that I can show actually what. Okay. So can you see what's written there? It's large enough? It's his associates. did allow that Djokovic I need the dot. If without the period, it doesn't work well. Oh, yeah, but it's too long now. I cannot see. It's completely mangled. I need a smaller sentence just that we can see it.
Can you use the font size?
Yes, I can reduce the font size maybe. But you don't see anything. Oh, it's still OK. So let me copy the sentence again and start again. Yes. Let's see. You have all the words here. And these are the parts of speech tags. And this is an initial chunking, like B means begin, E end, and NP noun phrase, verb phrase, and everything. So that's entity. That's the name entity recognition. So it recognized that so begin person, end person, Gebhard Grich, and Djokovic is a person too, but a single word. These are the verbs, and recognized by the post. Did allow, well, it's not too good, but in principle, I had this strange option that represents all the verbs like this. And let's see. Then the various columns describe the various arguments of the verbs. So the first one is guard. So they say that guard is the verb here. The argument number 0 is associates. So guard is somewhere, there is a dictionary that says the argument 0 is who is guarding. Then guard what is argument 1? The details of his training program. And then as though they were nuclear code is an adverbial thing, and the rest is not relevant to that verb. Now you have where, here. So where? Subject is they, which is where, okay. Basically, they were nuclear codes. So you understand that they and nuclear code is the same thing, is the argument 1, because it's the same list. Now you have did and allow. So somehow it's a bit of a mix, because they should have been different. Did allow, so it's probably did allow prefers exercise. Okay, so the did, I don't know what it did, because it was not supposed to do that. So anyway, who did? Gebhard Grich is trainer, it's sort of right. And did what? It's allow that Djokovic prefers to exercise outdoors. It's quite good so far. This one is screwed up because it makes of did and allow. So allow is things that who allowed is associated guards the details. Actually, that's quite right. The associates who guard the details, they're part of the guys who allowed, and the Grich is, yeah, okay. He thought that everybody allowed and not just the trainer. And allowed what? That Djokovic preferred to exercise outdoors. Then prefers. Who prefers Djokovic what to exercise outdoors? Quite good. And exercise. Who exercises Djokovic? It's quite good. It's not. And outdoors, he thought that was a kind of object. Or it's not right. Yes.
It says that they and nuclear codes are the same A1 for the verb.
No, it didn't say that. It doesn't do this kind of resolution. It's a tagging. It doesn't have the resolution. It didn't say that they. They and nuclear codes actually did because of where, which is a bit special when you have a verb like to be.
So somewhere is written that where implies that it's the same stuff.
It's written nowhere. It's all a big fat neural network.
But he's learned somehow.
He's learned it, yeah. You want to type 1? Somebody comes and type 1, just to show that I'm not cheating. Or you can invent your own, but actually it's nicer when you get something of the same kind of literary English. No, somebody, so be brave.
Well, just a question, actually. So, but when you do train the neural network, you have to give it such examples, not the same example, of course, but sentences, and you have to identify these things as
The auxiliary task was Wikipedia is unsupervised, or the supervision is what I did. You take sentences in Wikipedia, that's positive. You change a random word. You change the central word of the segment by a random word. You say it's negative, and you train that for months. Then when you do that, you get an embeddings that you're going to use as the input of a time delay network. Actually, it's a convolutional network that's going to output the classes that have been labeled on the tree bank and pen bank and prop bank dataset. Actually, this is a parse tree with the parentheses. You don't see it very well, but the newest version of this also produces a parse tree. So if you try to write this with a tree, which is an exercise that I'm not going to do reliably in front of you, but if somebody wants to, I'll be very glad. Yes? Well, that's part of the trend data. That's part of the main task. I use prop bank and so on, but it's just 1 million words. So the unsupervised part is about 1,000 times bigger. And if you don't do the unsupervised part, it's not working nearly as well. Okay, I want to do another one just for the kicks. Yeah, Ronan worked a lot on this, and it's working even better than he used to now.
Compared with other systems?
I'm going to come to that. Let me type a sentence. Okay. Hayes believes that the term partisan oh. Where is it? Oh, well, I'm going to stop here because there is a colon in another sentence. Okay, so what do we have? Or maybe I can do the parsing this time. Okay, so named entity, Hayes is a guy, Republican Party is an organization. That's good. You have beliefs and is, and isn't, didn't get. He thought it's a noun. Too bad. So believes, Hayes believes that the term partisan isn't particularly useful, blah, blah, blah. Good. And this is, the current Republican Party is a historical anomaly. Good. So he missed one of them. If you look at the parsing, so we try to build a tree. You have S is the sentence. You have a noun phrase, which is Hayes, a verb phrase, which is everything else, it seems. That inside you have this S bar thing, which is a sub-sentence here, with a noun phrase, the term partisan. He got confused by is, didn't see it's a verb, so it's messed up here. Useful in this era, he didn't see it's a time. And then you get another grouping here because the current Republican Party is a historical. So it's quite good, actually. It's not that bad. Oh yes, I'm going to show you something else. That's a code. So we have 3,500 lines of C total for all these things. There is no library, not everything is there. Actually, there is a library, it's BLAS. And then you have data files, and the data files are things like, actually it's in data. They're here, so you have a couple megabytes of data for the weights and hash. The hash is actually small, it's the hashing the words to, okay. Let's go back to the talk. So what's interesting is to look at the embeddings, how the words are embedded. And so we take in this embedding space one particular word, so that is frequency. That's the rank of the word in frequency order. So France is apparently more popular than Jesus, which is more popular than Xbox. And these are the closest words in the embedding space. So France is closest to Austria, Belgium, Germany, Italy, Greece, Sweden, Norway, Europe, is good. Jesus is close to God, Sati, Christ, Satan, Kali, Indra, Vishnu, that's quite good. Xbox is close to Amiga, PlayStation, MSX. PS number, every number was replaced by this number thing in capital letters. That means PS3, PS4, the thing. HD, the Unicast, okay. Reddish is greenish, bluish, pinkish, bluish, silvery. Scratch is nail, smash, punch, okay, fine. And megabits, okay, so megahertz is probably wrong here, but not too bad. It's not perfect, though. The tagging speed is above 10,000 watts per second. It's a big fat neural net running blast. There is no back propagation, no thinking, no going back. It's just feed forward and end of it. And if you look at this against various benchmarks, well, on parts of speech is state of the art. On chunking is state of the art. On entity recognition is state of the art. On parse tree level 0 is not too bad. On the semantic role labeling, which is this task of giving the arguments and everything, is a little bit worse. Not that much. But if you compare the speed, so the post system, the ones that we could get our hands on, they take in RAM something like 800 or 2 gigabytes. They run in something like 64 seconds to 5 minutes for a sentence, while we do actually 4 seconds. I don't remember what was the benchmark. It's not the Bible. The Bible is more than 4 seconds. Anyway, and 32 megabytes. If you do at the semantic role labeling, which is to say which are the various parts of a verb, you go from something that takes 2 hours and 3 gigs to 124 megabytes of RAM and 50 seconds. So the difference is that even though these guys have systems that have been optimized and everything, they do symbols, they do trees, they do pointers, they do hash tables, they do plenty of things like this. We do BLAS. No. So we have a kind of hardware advantage. It's good for the hardware. And this could be used on large-scale data very easily, discount. So now there is the question of, if you look in the deep training literature early, there is this notion of pre-training the neural net with unsupervised, yes? You don't.
How to choose them that you are sure that after 1 month it works?
Well, you look for the first week until you are happy that all the initiation, all your gradients are flowing properly, and then you let it go. And then if it stops training, you stop it, you save the weights, and you change a little bit of something, and you go on. Sometimes you do a little bit, but not very often. Maybe it was changed 2 or 3 times over. Actually, it was 2 months. The last month, Ronan was on vacation, so nobody changed anything. And before that, he would look once a week. And optimizing the number of units, the number of layers, everything, don't count on it. Don't have time. Yes?
And the learning curve, does it go like nicely smoothly, then saturate? Because that's what I'm wondering. So I also have something that's running nicely.
I don't have them. I remember they're not that smooth. You can have a stable for a time, then a jump, and then it goes somewhere else. And it never really goes down, but jumpy progression is possible. Yeah. Yeah, it's okay. It's the way it is. So in the deep learning literature, you see this idea of sequentially pre-training successive layers using unsupervised techniques. And in the case of, if you just feed forward, because this is the only thing I discussed in all this series of lectures, you have the noisy autoencoder, for instance, where you have a network that has a shape like this. So you would say the kind of thing that Yoshua Bengio would do, and Pascal Vincent is. So you start with some input thing, then you put a layer there that could be large, and another one which should be the same as the input. Then you inject noise here. For instance, one noise that works very well on text is to delete half of the words. And you want to reconstruct the complete bag of words, for instance, on the output. And you train this that way until you get a representation there. That's a representation of this bag of words that allows you to reconstruct the initial one or an approximation of the initial one. Then you remove this. You create another you threshold. You create another one like this, and another one like this. You apply noise on this one, and you train now this new auto-associator to reproduce at its output the unnoisy version, the denoised version of that one, and you get a new representation here, and you go on. and you keep generating layers like this. At the end, you take all the layers and you put a classifier on it, and you try to do what you wanted to do. So the idea is that there is something magic about unsupervised. And I think what's magic is that if you remember the check reader, we carefully selected subtasks that we thought were meaningful. And in fact, that was probably overkill. It seems that choosing subtasks that are unsupervised, I already do quite a good job. And I call these subtasks because I don't believe in unsupervised. So a remark, this is less popular than it used to be 2 years ago, because now they had progress in the optimization algorithm, like using Martin stuff and everything, so they can train deeper network directly, completely supervised. They do that a lot less. All the ImageNet success was done without that, because they had labels. So if you do unsupervised learning, you can wonder what is a cluster. The prototype of unsupervised learning is clustering. And somehow there is the assumption that the shape of the density reveals the underlying categories. Like for instance, you have the blue category and the yellow category, you have the base boundaries. What you don't see that I followed the red curve here and the blue one here, they're just hashed. And the base boundary is the point where the two distributions are equal. And when you see this yellow thing without knowing blue and red, you say, aha, maybe there is a blue and a red there, or maybe other colors, but there might be two classes. Seems very appealing. But suppose I transform the input space. I'm going to apply a differentiable transform of the input space that's going to compress things here, move them here, and expand things here. Now I have something like this. If I have my two distributions here, they overlap apparently more, but with the same probability still. And my two classes still exist. I still have a base boundary. But if I superpose the two distributions, I don't have clusters anymore. They're gone. So what does it mean about clustering? It means that clustering is an expression of the prior knowledge encoded by our choice of input representations. If you change the input representations, even in ways that are continuous, you can make cluster appear or make cluster disappear. Now, input representations, images, pixels, so it's very natural, and pixels in RGB space. Turns out that our eye doesn't produce a square grid of pixels. The density of receptors is higher in the middle and lower in the side, and the density of color receptor has an even different distribution. They're distributed quite randomly. So what's natural? The square grid of pixels in RGB space linear, or something like our eye with different density, probably log encoded? Are they going to give you the same clusters? Don't know. I wouldn't trust it. So for me, unsupervised learning is really very cheap labels. I just say that X1 and X2 are close because they close in the representation space I've chosen, or they're not close. And in fact, some embedding methods, or unsupervised learning methods, the ones of Jason Weston, for instance, and also some of Jan, are based on this idea of creating the pre-training not by using a strictly unsupervised criterion, but by using an information about whether two examples are close or not. So you actually create embeddings that represent your notion of proximity of examples. So, okay, unsupervised learning is just another task. Doing something on Wikipedia or something on which you have plenty of labels, same thing. It's not fundamentally different. It's a way to use label or information that you have on the side that's very cheap. And of course, the question is, how is it connected or not? We're going to come back to that. Now, that takes us to something that's very prospective. I tried to put this in a tech report, and I'm not completely satisfied by it. So take this with a grain of salt. So what we did here is transfer learning by rewiring. In the example number 1, we had this dual thing with taking two images, computing transformations of the image in the representation space, comparing them. Then I take just this part here, I rewrite it, I put a classifier, and I say this is John. Maybe I should have written Bernard there for a change. Or in the case of Ronan, you have this word embeddings. You have the sentence with the word in the middle that could be replaced by a fake one. Okay, I'll jump. And then you have a kind of TDNN that says this is a score of a good sentence or not. and then you take these word embeddings and you put them into a bunch of convolutional networks that's supposed to do the other tasks. It's a rewiring. Now, when this rewiring works well, you can try to take a Bayesian perspective again. You can say that the modules are parameterized by distributions, and you want to know the distribution of the weights instead of the single value. So when you train the auxiliary tasks, the problem is that when you compute the posteriors, they do not factorize on the modules very well. So you have to project them on the module to have a distribution that's projected on factorized space. But when you train the MES tasks, you can say that the posterior of the auxiliary task becomes the prior of the new task. And you could try to say that it generalizes better using some pack-based theorem. That doesn't tell you, okay, so that's going to give one of these results of learning theory that tells you, by doing things this way, you can generalize better, and maybe you're not going to be that much worse. Now, it doesn't tell you which transfer strategy will work best and which problem will transfer best, but tells you that in principle, this is not silly. Now, you can see the rewiring process an algebraic operation that operates in two space. When you rewire your modules together, you're changing the statistical model. You take elementary models, you're building a more complex model. And the model means the model without the parameter. The parameters are in the air and should be optimized by learning. But you also do that for the model realizations, which is a particular parameter, then the model is just a function. You compose the functions, you get a new function. And so you work in these two spaces with various operators, and you transport the functions and their parameterizations. In particular, if two ways are supposed to be equal, they're still supposed to be equal. And that gives you a structure in the parameter space, and I claim a structure in the space of questions, because in the case of the face recognition, I have a question which is, are these two faces the same thing? And by rewiring, I'm going to do something that's going to answer a different question, which is, who is this person? So this kind of structure, manipulations on the various modules, this is an expression of the semantics. And in particular, the secret algebra is very close to a semantic equation, a structural equation model of Perl. So somehow a secret algebra is different from a Bayes network because it's a causal semantic rather than a probabilistic semantic. So it's quite interesting to look at it this way. Now, if you want to enrich the semantic, well, look at your mathematical book. How do you make a nice algebraic structure? Well, you make it recursive. So, in fact, it's been done. It's been done as early as '88 by Jordan Pollack and then Jeff Hinton in the '90s. So, you have a representation space. We're not going to say what it's going to represent. You have an associational module, takes two vectors, produce a single vector, and this association takes one vector, produce two vectors. For instance, take the cat, you code them into some representation space, you associate them, you get a code that represents the cat that you could decode as the cat, maybe. And you can do it recursively. If you have sat on the mat, you can group the mat together and on the mat and sat on the mat. And if you apply the decoders, you're going to reconstruct. So somehow the dream there, and it works only in very small setups, is that the code represents pretty much anything. It's the state of your brain, if you want. And then you have some invariances. You want that the dissociation of the association of xy should be xy, which says that this is an algebraic invariant that you want to enforce either by training or by construction. And you can build what Jordan Pollack said in the 80s is that using this recursive auto-associative memories, you can represent infinite depth predicates, a little bit like the Korn-Scar CDA operators of list processing. Quite amusing, but it's not true because it's up to numerical accuracy. You're using a vector space, which is, well, actually, in terms of entropy, if there were, it would be infinite, but it's not practical. So if you have a numerical vector space, which is R100, the numerical accuracy will eventually degrade reconstruction. And if the embeddings in the representation space make sense, you're going to reconstruct something that approximates. There's going to be an approximate sentence, something close. So somehow there's this property that humans have that if I tell you something very long, like a lecture, hopefully you'll be able to reconstruct an approximation, but not my exact words, unless you're a kind of particular person. But this property is interesting because you see it in these kind of structures. And of course, you can define ways to try to parse, except that this doesn't work so well. And you can train it in various ways. So Richard Socher recently did a lot of supervised training. And Ronan and others in NEC, we tried unsupervised. We got some interesting things that now we have embeddings for pairs of words. And last year, first year, same year, first day, third day, they grouped together red house, French house, rock house, red coat, the city, the town. It's quite nice to group together parts of sentences. But there's a lot of problem. It doesn't scale very well. It doesn't induce good parse tree. There is a good idea that's missing, meaning that if you try to reconstruct what reconstruct the best, to find the way to group together things in a way that reconstruct the best, is not going to give a very useful parse tree. There is a good idea missing there. I have my ideas about this, but they're not even close to be ready. And you have another problem, which is the grounding. Like sometimes red car, blue car, yellow car, or black motorcycle, they close because you could use them in sentences in a way that's similar, except that if you say the robber left with the red car, it's not the blue car. It's not close. So depending on where you are and what you mean, a single embedding space and a single non-trivial proximity is completely wrong. So you have to think about that too. Anyway, I'll give you a conclusion. So the exploitation part of the conclusion is that given the speed at which things are going now, and the fact that computers have reached this critical point, you can be certain to see lots of neural net applications in the coming years. And in particular on the perceptual task is probably going to be quite good because they really work well on this kind of tasks. On the exploration part, well, the statistical machine learning research program is the following. And it's something that you see very constantly. Discussing the models, like the approximation properties. Can a neural networks approximate everything? And the answer is yes, with certain conditions. Discussing the loss function, like asymptotic consistency, surrogates, and everything. Discussing learning algorithm, optimization, large scale, how they do on test. And discussing generalization, like capacity control. This has been done. Well, you have refinements, of course, you can do plenty of things, but this program has been pretty much done. So my personal guess is that we have to go elsewhere. We have to go further. And the way I would do it, but this is personal again, is that I would study a different kind of object, which is not a single statistical model, but a collection of statistical models with different input and output spaces, connected by some transformation or an algebra of transformation that explain how to transfer knowledge across models. Now, training examples, they can pertain to different models, each of them. Test examples as well. The glue is the algebraic structure. And it's connected to reasoning, so I find it very exciting. Now, it's awfully hard. So if you get a good idea, please go on and go. I'll be the first one to upload. Thank you.
So questions? Any questions? Are there any questions in the observation lounge? Then I still have a question.
No, we don't have any questions.
I didn't get completely what you are planning to do now here in the next time.
I wish you told me, because I'm not completely sure. Like a couple of years ago, I wrote an archive tech report trying to outline a research program in that direction, but I got shaken because of this thing, that this doesn't induce good parse trees. And there is a couple of good ideas missing there, I think.
So could you get a concrete example of what kind of problems you would be able to solve once you're done with the new stuff?
Well, if you were done with this new stuff, you could do this. So you could take text images and try to parse them, meaning that you're going to group things together in a hierarchical way that makes sense. So you could take a text and compute a parse tree, and doing it unsupervised is a big problem, and this is what doesn't work too well. Or you could take an image and build a parse tree that not only find objects, but find their relations. I want to know that an object is in front of another one, and vice versa. Then you get a space representing images and scenes, and you can try to define operators in this space, which is what's happening if I change my point of view. Like, for instance, here I can see Matthias' label, and here I cannot. But if I go back here, I know I will see it again. And this kind of thing is something very essential in the way humans and animals move and live. And we built a model of that. We know I know that if I move, I know what I'm going to see because I've seen it before, and I've learned that there are some invariances. And there is also a lot of psychological evidence about how these invariances are acquired. Like you have the invariance of the object, which goes back to Piaget experiments in the 30s. So can I do that with a neural network or any kind of machine learning, by the way? It doesn't have to be a neural network. And that's something quite interesting. But it's also difficult to do because the empirical setup is complex. If you look at machine learning during the last 30 years, progress was driven with the idea of having a training set and a testing set, and that's simple to test. Now, these kind of things are more complicated to test and measure. I think we have to be a lot more subtle now. Yeah?
So about your final slide, I think a very interesting class of statistical models to study is the class of models that you get if you consider a structural equation model, consider certain things as invariant and others as noise or exogenous variables, and you study the family that you get as you vary these other quantities.
Correct, that's one.
And the algebra connecting the different things is given by the framework of structural equation models. So that's a pretty concrete
that's one of
thing
them
that goes in this direction.
There are examples of this. Bayes nets are this. When you have Bayes nets, you can see them as models of plenty of conditional distributions, and they're connected by Bayes rule.
But that's not the same as what I mean, right?
It's not the same model.
Okay.
It doesn't have the same properties. So then you can wonder, how many of these models are they, and how to classify them? And so you could say that first-order logic is something of that kind too. And the Markov logics of Pedro Domingos are something like that too. And the causal ones capture something that the pure Bayesian ones do not capture. And if you look at the spatial one, where I'm just moving around and my operators are changing my point of view and how my image is changing, which is at a purely perceptual level, is a much simpler one, but could be very useful for applications. So the same way we have a menagerie of statistical models with various properties that we start to understand, you might have a menagerie of this kind of reasoning models that have various properties, and we like to know how they generalize, how many categories there are, what are they doing, how can I, it's wide open.
Great, there are more questions.
I was just wondering, so one direction that is probably a bit limiting is the user-friendliness of all of this, right? So you need to know a lot of tricks in order to get things to work. So, I mean, recently there have been quite a few groups trying to automatize that by doing Gaussian process optimization and
in Bayesian optimization.
Yeah. So what do you think about this direction? I mean, they are not there yet, but it seems like if somebody could use outside of the circle of a few people and could really make this work.
It's too bad Philippe Hennig is not here. Yeah, Philippe has a lot of things to say about this, a lot more than me. I think it's interesting. I just don't know where it's going to go.
So have you used this as well?
I didn't use it because, frankly, it's not that user-friendly either. You have plenty of tricks and things to do to make them work well, but you know where it's going to go. I'm a strong believer in trying to understand what you do at the lowest level. So I don't want to use a black box that somebody else wrote. I want to understand what's inside as much as possible. And if you do neural nets, I would recommend to do the same. You can take an existing code, but understand how it works, because if it doesn't work, which could happen very easily, you want to be able to diagnose it. You want to be able to see, oh, my gradients are completely zero in that part of the network, and I need to do something with my initialization to change it, and blah, blah, blah. You must keep your eyes open. And yeah, I think that's very important. Somehow, it's the scientific approach. You should look at these networks. Sometimes you're an engineer because you're building them, and sometimes you're like a biologist because you're going to try to see what works and what doesn't work, and then you switch between the two roles. Yeah, okay. Maybe that was not very deep, but...
I have another question. So I'm completely clear about your training regime in the NLP paper. So you basically trained on these Wikipedia, on this Wikipedia data with the one-word exchanged, and then after that went to labeled data with.
I think maybe this is the one. This is the Wikipedia training set. You have these word embeddings where you represent each word by a 100-dimensional vector. And you input them as input of a convolutional net, and you have this scoring thing. You want the score of the correct sentences to be higher than the score of sentence where you change the middle word. And you train that forever. If you train this, it's going to tell you something interesting, because to some extent it's going to tell you which words could go at this point in the sentence. So you get a classification that's quite interesting. You don't know where the threshold is because it's a ranking, which is a bit unfortunate. I would like to know it for some applications. Then you take these word embeddings and you put them as inputs to a bunch of convolutional networks that are supposed to do these various tagging tasks. And you train all that thing together. Actually, you can train them separate or together. If you train them together, you get a little bit of multitask benefit. And when we train them, you can even leave this fixed or let them train. If it's fixed, it doesn't work as well as if you let them move a little bit. And if you train them separately, it's better to let them move separately. Then if you want to do the demo, you can do some sort of engineering tricks, because here it's pretty much pure system. So you can say, well, I can use the part of speech as an input to the indemnity and the chunking, and I can use the chunking and indemnity as an input to the SRL. But there is still no real feature extraction in the sense of feature extraction of the NLP people. You know, there is no detection of verbs, detection of passive voice, detection of... typically, the NLP system, you have an army of PhD students invents features that are binary, and then you induce some kind of a tree, you compute the features everywhere, you run a bunch of SVMs, and you try to decode the result as tags using some integer programming or something like that. So it's quite different in its approach. It's interesting that this technique, which is very brutal in a certain sense, works very close to the state of the art with interesting properties. Now there are similarities too, like the decoding, which is the decoding of the networks. This one, the decoding of SL network, is the same kind of thing as the decoding of the check reader. So it's close to a CRF, and of course they use CRF, so that's a connection. Yes?